Well, I can't start this video out with a look at Chuck Penson's book because this video is not about a piece of Heathkit test equipment. So, for the history, I'm looking at this is the 1975, one of the 1975 Heathkit catalogs. This is like a false outer cover. The real catalog starts here. And this is identified as the Winter 1976 catalog. And normally they trumpeted new items right inside the front. They didn't always do that, but in this instance we have this nifty looking digital stopwatch. A new standard for versatility and value, Heathkit digital stopwatch. $99.95, used by coaches and timers of the United States International Skating Association, which is kind of interesting because this appears to be a brand new item and it's already in use by a skating association. Or maybe they just mean that digital stopwatches are used by that, not this particular one. Who knows? If anybody does know, please put it in the comments. So 7 functions, 8 digits, 1/100th of a second resolution, and typical accuracy of plus or minus 0.003%. All the range and accuracy you'll probably ever need, just 1/100th of a second, and all the way up to 99 hours, 59 minutes, 59.99 seconds, with quartz crystal precision. 2 exclusive Heathkit designed PMOS IC counters give it versatility never before achieved. Well, I'm not sure that Heathkit designed any ICs ever. And indeed, these ICs that are used in here are all ones that were just normally sold by semiconductor manufacturers. But it's possible that Heathkit might have approached National Semiconductor and said, hey, we'd like you to design a chip for us, and then they did it. So they may have had a hand in the design by writing specifications or, desired functionality, and then National just came up with a new product. But it isn't Heathkit exclusive for sure. That part has been available for, the mid-70s. Anyway, its wide range of functions makes it ideal for almost any timing job, from navigating an airplane to timing a race. Function 1, start, stop, elapsed time, times any number of individual events, while also counting the total elapsed time from beginning of first event to end of the last, like 2 stopwatches in one, times 2 participants in the same event, ideal for races. Function 2 is sequential, times and displays each part of an event, for example, each lap, while also timing the overall event. Compare lap times of any participants while still timing the overall event, ideal for multi-lap races, navigation, etc. Function 3, total activity time, accumulates elapsed time for series of events, also maintains separate count of total elapsed time, including downtime and breaks, perfect for auto or plane trips efficiency studies. Function 4, split, displays cumulative time to each split point while continuing to time overall event, useful in ski races, swim meets, sailboat race, committees, etc. Function 5, start-stop activity time, shows separate times for each event or leg, then totals all individual times. Great for trips, races, rallies. Function 6, upcount, counts to programmed or learned time, then sends a trigger pulse to the alarm jack. Same number can be used repeatedly without reprogramming, and count can be interrupted and resumed at any point. Perfect for timing tests, officiating, etc. Function 7, down count, counts from programmed the number to 0, then sends a triggered pulse to the alarm jack. It doesn't actually send a pulse, it sends a continuous signal, but okay. Count can be interrupted and resumed at any point, ideal for yacht races, testing, officiating, and helps athletes pace themselves in training. Functions 6 and 7 are unique. The stopwatch can learn a time in one of the other functions, then transfer it to function 6 or 7, or program any time up to 9 hours, 59 minutes, 59 seconds using a clever digit set method. Start-stop jacks for photoelectric and relay circuits. Display switch turns the readoffs off in functions 1 through 5 to conserve batteries, and in functions 2 and 4, switching off then on unlatches display to show counting process. After an event is finished, pressing the start-stop button alternately displays time in each counter. High impact plastic case. The price again is $99.95, and you can get a felt-lined naugahyde carrying case for an additional $3.95. Battery life is approximately 40 hours between charges, assuming the displays are off most of the time. Approximately 4 hours battery life with displays continuously on. Recharging takes about 14 hours with the power turned off. Temperature range is -10 to +120 degrees Fahrenheit. Weighs 8 ounces. And there they show the removable sunshield. They show the lanyard and the AC adapter charger. And they show the 3 jacks that let you connect up external circuitry and the charger. And in the Christmas 1976 catalog, it's now on a black and white page. Still the same price. Still the same naugahyde carrying case. There's several different versions of this product. There's the regular GB-1201, and then there's a GB-1201E or -E, which is for export market, and then there are special versions of those, like the one for France. And I haven't been able to nail it down for sure, but I believe that the one that's EF is export market France, and probably the main difference between that and the regular export market version is that maybe the manual's in French. That's all I can guess. The export market versions have a different power supply or charger. The one that comes with it normally is only 120 volts AC. The export market one substitutes the power transformer in the charger with one that runs at 220 volts. Well, I found one battery that looks like it's a close equivalent. It's on batteryguy.com. This is the product listing. I'd sent them photos and dimensions and things like that, and they came back and said this was a near equivalent. So it is NiCad. It is 7.2 volts. It's 900 milliampere hours, even though you think a battery company would know how to represent milliampere hours. It's not all lowercase, it's not all uppercase. There's a specific way that's right. They didn't get it. So they have this part number BGN 800-6SWP-Mini-9030EC, rechargeable. Its dimensions is in the length it's 3.82, so slightly less than the 4 inches of the old pack, and about 1.69, which is, you know, almost exactly right for the width, and then the height is, you know, half of that. That should be about right. And the price seems reasonable, so that's what I'm going with. It does have a connector on the end, which I'll have to cut off. Alright, let's take a look inside the unit. I've been doing this so piecemeal that a lot of parts aren't going to add up chronologically in the video. I'll try to explain as much of it as I can when I notice discrepancies or confusing parts. So this is the bottom of the unit. It's quite deep because it has to hold the old school NiCad battery pack, 6 cells, adding up to 7.2 volts. This is a very close replacement for the original. It probably has greater milliampere hours than the original, but it's the same battery chemistry and voltage and physical size. It comes with this plug, which is way too big. There's not going to be room for it. I'm just going to have to splice the wires into the small ones that I cut off the original battery pack. So there's that, and then you've got the front of the case with the red window for the LEDs to go through, the front panel with the couple of switches, power and display on and off, and the function select and the reset button. So there's only 2 ICs on here. One of them is this one is a National Semiconductor CD4511, although Heathkit calls it MM14511. The M prefixes Motorola, and Motorola, when they put their own part numbers on generic parts, they tended to add a 1 in front of it. So the normal number 4511, coming from the CD4511 National Semiconductor part number, then they add the MM1 in front of that, which makes it confusing because then you're looking for 14511 when the only important part is the 4511. Anyway, it's a combination BCD to 7-segment converter. It also is a segment driver for the 7-segment LEDs, so a couple functions in that chip. And then this is a DM8863. That's, I think, a Motorola part, although it's marked National Semiconductor, and it's still DS/DM8863. And that's just a digit driver, so there's 8 signals going through this. Each one goes to the common of the 8 digits of display, and this one drives the 7 segments. There are no decimal points in these displays. I think these are probably National Semiconductor parts, but when I looked up the part number, which is not given by Heathkit, I have access through somebody I know to the Heathkit master parts list, a huge computer printed document that tells every part number they ever had, and you know, its characteristics, its pricing, you know, how many they have in stock at the time it was printed, and all sorts of things like that. And you know, a part number that you can figure out what it really is, in spite of what Heathkit sometimes says in their manuals. And so I was able to dial down to a National Semiconductor part number, and they do have, I mean, they originated these 2 chips, and then other companies copied them. They made them generic. And this particular type, these are like the old school 1970s calculator LEDs. They're very tiny, and so they have these thick magnifying lenses over them, but they're really just these little plug-in modules. And there's 2 modules side by side here, and 2 modules side by side here. Each one has 3 digits, as you can see. Let's see if I can get it without so much reflection. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. They're offset by about 1 digit sideways between the 2 of them. So there's actually 4 modules with 3 digits per module. And the physical look and everything adds up to the National Semiconductor parts, but it wasn't an exact part number, and that's because I was able to download the full National Semiconductor data book from 1977, and they have a plethora of these displays with all sorts of options and you know, they don't have one natively that has only 3 digits per chip, if you will. They have ones with 2 digits, they have ones with 4 digits, but they will custom make you ones with different numbers of digits. And that is apparently what Heathkit did. They had a custom order from National to make these. So if you blow these up, you're in trouble, because they're not a generic part that you'd likely find anywhere else. These chips, on the other hand, are probably still available if they turn out to be bad. This switch here is the power on-off switch, little slide switch. This one is the display on and off, so to conserve battery power, you can let the thing run, but not be powering the LEDs. So this just turns the LED part of the circuit on. Then, of course, this is the reset switch here. And up at the top of the board is, well, it's kind of hard to see it, but there's a resistor there. That's the charging resistor for the NiCad battery pack. And inside this piece of shrink tube is a diode. And that's just a safety diode going to the power jack in case you plug in something with the wrong polarity or something like that. It prevents you trying to charge the battery with the wrong polarity, which could start a fire, etc. And also blow up stuff inside the meter and inside the counter. There's 2 fuses in here on either side of the battery when the battery gets wired up. And this is one thing that's kind of interesting about it. There's this little piece of wire there. That's a fuse wire. And there should be one going over to here, but I don't see it. It's like that fuse wire was never put in, or if it is, it was blown. And it would blow if the battery pack is shorted out or something. But it does seem like there's a fuse wire missing there. So I'm going to have to wring that out and see if I need to put something else in its place. There's the 3 jacks. I think it's the middle one. Let's see. Yeah, the middle one is the power jack for the charger, which is just a regulated 9-volt DC wall wart of some kind, good for 100 milliamps, so no big requirement. Oddly enough, I was able to find exactly the right part on Amazon. I don't know how old the stock is, but it had the right voltage, plug type, plug polarity, current rating, as what Heathkit specified. I'm waiting on that to come in. It's not something Amazon stocked, it's a marketplace order, so anyway, it's nice to know I don't have to jury rig something for that, but this won't work if the fuse wire is missing or blown, so I have to investigate that. So here's the main circuit board. This other one is the display circuit board that I already talked about. And it has the 2 switches on here. These go out the sides so you can easily operate them with your thumb and middle finger or forefinger while you're holding it. And these are good quality, like cherry switches, so they're not cheaping out here. I think they tried to make this a serious piece of equipment. So one of those has to do with like laps and things, and the other one is a simple start-stop, and you use them in various combinations depending on the function you've dialed in on the front panel, how you want the counter to behave and what type of counter you want it to be. And then there's a transistor in here that's just this black part that's leaning over so it won't hit something else, and that is something that's taking in a signal from one of these outer jacks and inverting it and feeding it into the ICs. These 2 ICs are identical. They are not marked with the manufacturer's part number. They are marked National Semiconductor, and that's who originated the chip. But these are, well, Heathkit calls them MM5865s. Again, that sounds like the Motorola version of it, second sourcing these parts, but these are marked National Semiconductor. But I think the key there is 5865, that's the key number. These are monolithic, do almost everything in a chip, counter/stopwatch ICs, and they're identical, although these seem to be from different batches. But they are both the 443-693 Heathkit part number. This one's marked 530, this one's marked 531. The color of the plastic is a little different. But these do pretty much everything. That's why the complexity of the circuit is mostly just done here. And then it needs a little help from the display driver chips on the display board. But pretty much everything else is done in these two chips. And a lot of them, they can be used individually if you don't need such a fancy counter. But you can use them in parallel or in tandem with each other. And indeed, I've traced out the schematic against the recommended circuit for a stopwatch in the National Semiconductor Data Book. And a few bits here and there that are different. Heathkit, you know, added a couple more functions. The data book suggests 5 functions. Heathkit has 7 functions on this product. In order to get those functions, they had to do some games with diodes. Like there's a diode there's a couple of diodes over here, there's this down here, these 2 diodes here. Those are things that Heathkit added so that they could kind of fake these chips out and get you a couple more variations on the circuit that the chips don't do by themselves. You have to interconnect their pins in various ways. So otherwise, a lot of the pins are tied together. All those ones in yellow, those are from the function switch over here, so they go over and branch over to here, they can branch up to here. There's some interconnecting so they can overflow one to the other. There's a couple control signals going back and forth, and those are these ones I've got in magenta kind of branching around. That's how the 2 chips talk to each other. Only the first one in the series has the crystal oscillator, and it uses its clock, and then the other one slaves off of that. Each one of them handles 4 digits of the display, and it can be set up, I think, so they're acting like an 8-digit display, or most likely and most commonly they're going to be 2 different 4-digit displays, each one meaning something different. Like one might be accumulated time and the other might be lap time. You know, you're timing a foot race, and you know, every time one of the runners runs past you, you click one of the buttons, and that'll freeze the one display so you can write down what the time was, and then you click that button, and then that display starts timing the second runner to come through. Meanwhile, the other 4 digits have been counting since the beginning of the race. That type of thing. So yeah, there's not much more to it. This is the function switch here. It's very small, but it has 7 positions. Very simple switch. It just has one common, and then it makes connection from that to 7 different pins on this. Right there. The 2 boards connect together with these pin headers. These are kind of old-fashioned ones, but they probably work. The pins look like they're gold-plated on the male side. These are like the old Molex style ones, but they usually work all right. Oh yeah. The crystal is right here, and then there's a fixed capacitor and an adjustable capacitor in the small picofarad range on both of them, and those are there to help stabilize and keep the oscillator running. and by tweaking the adjustable one you can make very minuscule adjustments to the crystal frequency to get it exactly right. So I need to investigate that missing fuse and see if it's actually in there somewhere and I just can't see it. And then probably I'll just have to short it out for the purposes of testing. I'll test it initially without the battery in the circuit and see if the rest of it is alive. Okay, I was looking in the wrong place. The other fuse wire is there. It is intact. It's right in the middle of the picture here. The angle I was looking at it before, the display was kind of occluding my view of it, because the other one is up further to the right and on the back of the board. So that's why I couldn't see it. Okay, because the circuit boards aren't screwed into the case, when I was pushing the load button it wasn't really making good contact, but it did work. I'm going to push the other button on the right hand side and see what happens. Nothing. Push the button on the left hand side. Maybe I put it in load mode. Let's see. Yeah, apparently I was in load mode. I haven't read the instructions yet, so I'm just guessing at the controls. Pushing the right hand button here freezes it, so it's at 1488. Okay. 089. It's like it's giving me two different results. I'm alternating between them. Push the reset button again. It's probably in load mode. Well, at least that much seems to be working. I can reset it. I can count up. I can push that button and stop it. And every time I push the button, again, it goes back to 0, counts up and stops. Resets, goes back to 0 and stops. I don't know. I mean, I think that the chips are working, but I haven't seen anything on the upper display yet. I do want to see that. Mode 3, Mode 4, Mode 5, Mode 6. Oh, there we go. When I get up to the additional functions like 6 and 7, now I get the second display on. Push the left button, see what happens. Okay, here's another test. I've read through the first couple of functions. I have to make sure the switch is in function 1. Turn the power on. Press the reset button. The display should be blank. Push the SS button. That's the one on the left that should start counting. When it gets up to about 5, push it again. It should stop counting. Wait about 5 seconds. Push it again. It counts up again. Wait till it gets around 5. Push it again, it stops. Wait about 5 seconds, push it again. And it should get up around 5. I'll push the other button, but I let it go by because I wasn't quick enough. It's almost 10 seconds. Okay, so now if I push the SS button, it reads about 75 seconds, is that right? Here's a pair of new old stock MM5865Ns. Alright, here's a first test with the those main chips replaced. So power's on. I've got it reset. I'm going to start a counting sequence with the start stop button on the left. Let it get up around 5 seconds. Stop it. The master clock will keep running. And then after about 5 more seconds, I'll use this button to start it again. And after about 5 seconds, I'll stop it. So I've got 2 timed, roughly 5-second intervals separated by a 5-second interval. I'm going to stop the second one by pushing the full stop button on the right. That will stop the master clock, or clock B as the manual calls it. And so the timing of the first or the second interval will be shown on the display, but then when I push this button, it's going to show the master clock, or clock B, which should be somewhere around 15 seconds, depending how accurately I use the buttons. So let's see if that works. It did not work with the old chips. Okay, 2, 3, 4, 5. 2, 3, 4, 5. Get my finger ready with the right button. Okay, so I've made 2 timings. Now it's showing the time of the second interval, a little over 5 seconds. If I push the left button, yeah, 17 seconds, a little bit longer than the planned 15 seconds, but at least it's doing that. It did not do that before, so it's definitely working better. So now I have to push the reset to clear it. So that's working. Let's just try it in function 2. The difference here is that it doesn't accumulate time in counter A the way the other one did. It's just doing individual laps or something like that with the left button in counter A, while counter B still does the overall event. So let's see, make sure we've reset, start it. I'm going to let it go up to around 5 seconds and stop it. I could record that number. I have some period of time here I don't care about. I'll just keep talking for a little bit. Now I'm going to push that, and it'll show the aggregate time. And then the second time, so it's sort of cycling through these things, but it's still counting. So now I'm going to push the right button and push the left button again, and I get a much bigger number. So it's a subtle difference. It's kind of hard to use this and explain it at the same time, but this is appropriate. I had a 37 overall interval there, and otherwise it's the same as the other one. It's how counter A, that's the one that's displayed here, works. So something else I didn't do correctly the first time I tried demonstrating this for this video, because I hadn't read the manual yet, was I thought that the upper display and the lower display were the 2 different counters. Turns out they're not. The lower 4 digits are small fractions of a second, like hundredths of a second, then the next digit is tenths of a second, then the third digit is seconds, the left digit is tens of seconds, and then it rolls over to minutes in 2 digits and hours in 2 digits. So let's see what happens there. I make sure I've reset it. I'm back in function 1. I'm going to push the button to start it and just let it go for a while. Have to let it go for a minute. Yeah, for a good minute before it'll start activating the upper display. Display is very clear. It's not very large, but it is very clear. Now, something this came with, which I don't have, is a light shield that would snap on to little recesses here and here, and it just had deep channels that would shield the light from top, bottom, and sides for each of the two displays. That's for if you're using it in bright sunlight. So we're getting up towards 1 minute here. "54 seconds. Okay, it went back to 0, and now I've got 1 minute there. So that is working. That also did not seem to be working properly before. I'm not going to try to demonstrate all the different functions because the subtleties are so fine that I think it would just waste a lot of time. I'll discuss what the differences are, but I won't try to demonstrate them. It's very small differences between them. While I'm waiting on that, I did purchase some 2.5 millimeter plugs from Amazon, and that's so when I get the charger in, which should come in a few more days, I know it's shipped anyway, then I can actually charge the batteries the proper way. So we're getting close to rolling over to 2 on the upper display. Two, yay! Okay, I'm just going to look through the manual quickly here and describe the different functions as they're described in the text. So function 1, that's the knob on the front panel. Function 1 is start-stop with total elapsed time. Counter B measures the total elapsed time of an overall event. It counts from the first SS button push to the first FS button pushed. SS is the left button, FS is the right button. So SS means start-stop, FS means final stop. Counter A is the one that we normally look at. It counts initially from the first push of the SS button. Further pushes of the SS button alternately clear counter A to 0 and restart it counting, and then stopping the counting in counter A, which is confusing as heck. But that's the one I demonstrated already. Example of that is you want to time 2 runners competing in the 440-yard dash at the local track. Shortly before the race is scheduled to begin, check to make sure your stopwatch is ready. Then as the starting gun sounds, press the SS button. Press the SS button again as the first runner, hopefully not your favorite, crosses the finish line. Oh, hopefully your favorite crosses the finish line. Press the FS button when the second runner crosses the finish line. The time displayed is that of the first runner. Press the SS button again to display the time of the second runner. Function 2 is sequential total elapsed time. Counter B counts from the first FS button push to the first FS button push. Counter A times individual events. It counts initially from the first SS button push to the second SS button pushed, but also clears counter A to 0 and restarts the counting again at the second SS entry. So there was a difference there between the first function, where if I pushed SS and then pushed it again, it would time the interval between those. Then counter B is still running, but counter A has stopped. I'd have to push SS again to restart counter A, and I could do that as many times as I want until I'm finally done. Then I would push the FS, the final stop button, and both counters would be stopped. And then I could look at either counter. The second function is it doesn't stop and wait to restart counter A. It immediately restarts counter A every time I push the SS button. So it doesn't leave that gap in between. But what counter B is doing is the same as it did before. And there's a long story to describe how you might use that. Function 3 is accumulated total elapsed time. Counter B measures the total elapsed time of the overall event, counts from the first FS or SS entry to the first FS entry, so the same as before. Counter A totals the activity of an event. It counts initially from the first SS entry to the second SS entry. Further SS entries alternately resume the count where it left off, then stop the counting in counter A. So, gives you an example. You and a pilot friend have planned a cross-country trip that includes an intermediate stop for refueling, lunch, etc. As you take off, you press the SS push button. Press SS again when you land at your first stop. The actual flight time accumulating in counter A stops, but the total elapsed time of your trip continues in counter B. As you take off again, press SS. Press FS when you land at your final destination. The time displayed is the total accumulated flight time. Press SS again to obtain the total elapsed time from the point of departure to the final destination. So a lot of subtleties. Function 4 is split total elapsed time. Counter B measures the total elapsed time of the overall event like it has in all the other functions. It counts from the first SS entry to the first FS entry. Counter A also measures the total elapsed time, but it provides an updated display of the elapsed time for each SS entry. So that's an important thing. Up to this point, we've never been able to see the total elapsed time until we're done with everything and we've recorded any of the shorter lap times or intervals, written them down on paper or whatever, but we can't see them until we've pushed FS and then push SS to view counter B. Here, both counters are measuring the total elapsed time and pretty much in sync with each other, but because they're doing that, you can see what's happening the whole time because you're looking at A and you know that B is doing the same thing. So, again, maybe not the most common thing you'd be doing, but function 5 is start-stop accumulated activity time. Counter A times individual events. It counts initially from the first SS entry to the second SS entry. Further SS entries alternately clear counter A to 0 and restart it counting, then stop counting in counter A. Counter B accumulates the total or the individual time intervals measured by counter A. It counts initially from the first SS to the second SS. Further SS entries alternately resume the counting in B from where it stopped, then stop the counting of the counter B. Counting is stopped when both counters A and B. Counter is stopped in both counters A and B on the first FS, final stop entry. So again, very useful permutations. Function 6 is programmable upcount. Two more functions, function 6 and function 7. And they're programmable. They're actually built into the ICs, but they're not really described by National Semiconductor in the datasheet. And when they show the sample circuits, they don't have anything in there to utilize these additional virtual functions. But it's those extra components in the circuit, the extra diodes and things that I'm pointing out elsewhere in this video, that allow this implementation of the circuit to have these extra functions. And so counter B stores a programmed number. Counter A counts from 0 to the number in counter B, whatever that is. It starts counting from 0 on the first SS entry. It stops and resumes count on alternate SS entries. Counting stops and an alarm output signal appears at the alarm output jack when the time of counter A is coincident with the time in counter B. And there's two different ways you can program the stopwatch counters. The digit set method allows you to set digits 1, 2, 3, 4, and 5, and those are shown on the front panel sketch in the manual, to a desired number. So you program each digit individually up to 5 digits. You cannot set the tens of hours, tenths of seconds, or tens of seconds, or hundredths of seconds using this method. Then there's the learn method that allows you to time a single event and then enter or learn the time into the stopwatch counters. So here are the 5 digits that can be programmed. It's not the hundredths of seconds, it's not the tenths of seconds, but you can definitely program the units and the tens of seconds digits, that's 4 and 5, and you can program the units and tens of minutes and the units of hours. Those you can program. So according to this, turn the power on, make sure the display is on, turn the function switch to function 7. We're in function 6 here, but we have to turn it to 7 to do this. Press the reset button, all zeros will be displayed. Push the FS button, that's final stop button. Turn the function switch to position 1 to set digit 1. Press and hold the SS button. Also, then press and hold the FS button. Digit 1 will repeatedly count 0 through 9, doing that count over and over again. Release FS quickly at the desired number, which would represent hours, because that's what digit 1 is, hours. When that number appears in the display, releasing FS to freeze it at that. Continue holding the SS button. Turn the function switch to position 2 to set digit 2. Press and hold the FS button. Digit 2 will repeatedly count 0 to 5, and so on. So that's the way you can program in a number. And on you do the same thing until you've set all the digits. Example, you have set up your camera on a hillside overlooking a picturesque city to take several time exposures at night. You use the stopwatch and one of the alarm circuits you have constructed to serve as a timer with an audible alarm. Before you take your first picture, make sure the stopwatch is in its ready state and programmed to the desired exposure time. Then press the SS button and open the camera shutter at the same time. When the alarm sounds, close the shutter, so you have to be there to do that. Reposition your camera for the next picture. Press the load reset button to reload the program time. Then as before, push SS, open the shutter at the same time, close the shutter as the alarm sounds. You just keep doing that over and over. Now the alarm can just sound an alarm, but it can also be connected up to a circuit you would construct that would operate a relay, for example, and from that, if your camera's shutter can be controlled by an external switch or something like that, you could actually have the timer control the shutter. It's possible to do. But this simple version of that has you listening to the audible alarm, which you would hook up to the external jacks, and then manually operate the shutter. And then function 7 is a programmable down count. A stores a 0, B counts down from the program number to the number in counter A. Start counting down from the program number on the first SS entry, or push, stops and resumes count on alternate SS entries that occur prior to the end of the countdown. Counting stops and an alarm output signal appears at the alarm output jack when the time of counter B is coincident with the time in counter A. So it's really just like the other one, except that instead of counting up, it's counting down. Here's a little sketch I made making the schematic a little bit neater. This is the SS jack on the counter, and this is the FS jack on the counter. they're not the same. It's like you'd think that the ring on the or the sleeve on the jack would be ground on both or V plus on both, but in fact V plus goes to the tip of SS and the sleeve is the output. So it's fed from the tip, and then if you have an external switch connected up to that jack, then when you close the switch it would allow V plus to go through it and continue on to the circuit. In that way it's in parallel with the SS button on the side of the counter or the timer. V plus goes here, V plus goes here. The output of that goes to the same place on this switch, and then it goes on to the IC. So hooking up a switch to SS jack does exactly the same thing as pushing the SS button. FS, the sleeve is tied to circuit ground and the tip is connected through a diode and back to the FS switch, but it's not the same simple two things in parallel that it is for SS. But it can still work that way. It's just a little trickier to figure the wiring. You have to assume that most of the time you're not pushing SS and FS at the same time. So if you're not pushing SS, V plus goes through the normally closed contacts of SS, it goes down here, and when you push FS, it goes down this way, through the diode, through another diode, and onto the IC. So this point becomes V plus. At any time when you push FS but are not pushing SS. Hooking up an external switch to this will pull this point low when you close the switch. And that's not the same thing as happens here. So it's a little confusing, and the best way to make sense of it is to look at the examples, of which there are several in the manual. If you just want to get the alarm, you hook up your jack with something like a Son Alert buzzer, the softer sound one that doesn't have quite as much of an amplitude, more of a quiet beeping, because it is powered directly off the internal circuitry through a 10K resistor. But if you need it louder, you could use the same Son Alert but without the 10K resistor. This jack cannot supply enough current to run the Son Alert at full volume. So if you need to do that, then you do it this way. The same jack comes out, you have a voltage divider here. It's also biasing for the transistor. When the signal turns on here, and that's a good point, I should go back to say that FS is an input as well as an output. That's part of the reason it's wired up this way. And here it is being used as an output. So it's not being used as a parallel FS switch, it's being used as an alarm output. So when the signal comes on, it turns on the transistor, and an external power source like a battery goes into the Son Alert and drives it at full volume because there's no current restriction. Whoops, yeah, my camera drifted. Basically, you're allowing the Son Alert to run at full current and therefore full volume under control of the FS jack. Here's a similar circuit if you want to use the FS jack to activate a relay. The transistor allows current to flow through the relay coil instead of through a Son Alert. Otherwise, it's the same circuit. Now this is sort of doing the opposite. When you want to control the FS or the SS by a separate signal, you use the same circuit, but instead of having the FS jack control the transistor base, the separate signal controls the transistor base. The contacts of the relay are then wired to the FS or SS jack to act in parallel with those switches that are on the timer. If you just want to have remote control of either the switch or both switches, you do what I already described. You just have an external switch connect it up to a plug, and you can plug it into the FS or SS jack, or if you make two of them, you can plug it into both of them. This shows how a set of normally open switch contacts are used to remotely control the FS function. It's actually using one wire from the tip of the plug in the SS jack and one wire from the tip of the plug in the FS jack and connecting them together. It has a big caution: never connect the center tip of the SS jack to the sleeve collar of the FS jack, because that would connect the plus and minus of the timer's power supply together and short it out. Alright, I've decided to try the count up function, that's function 6, and to also demonstrate and verify operation of the final stop or alarm output. I've rigged up one of my plugs here, just jury-rigged it real quick, with a 1K resistor and LED. I don't have any son alerts of the appropriate type to be powered from this circuit. I'm trying to keep this as simple as possible so I don't have to do a lot of setup. So let's see how it goes. I'm going to turn this on, push reset. I need to turn the switch to function 7, and I get all these digits up here. I have to push reset, puts them all to 0. I have to push the FS button and release it. Turn to function 1. And then I have to press and hold the SS button and press and hold the FS button, which will cause digit number 1 to start counting 0 to 9 and repeat, and I'll release the FS button when it gets the right digit, but continue to hold the SS button and then move the switch to the next position and repeat, only releasing the FS button when all of the digits are correct. Now it's going to take 2 hands, so I'm not going to be able to show that. I don't have any tripod or anything set up that'll get this appropriate view. I'll be back once I've done that. Alright, I've gone through that process, trying to set it to 2 minutes and 30 seconds. I need to go to function 6 now. And somehow I ended up with 7 minutes and 10 seconds. Okay, so I verified I've got this setting of 2 minutes and 30 seconds. Now I push load reset, which should load that into the actual counter. And now I have to, let's see, push SS to start. But before I do that, I'm going to hook up the LED. Okay, so I'm going to push SS to start. So it's counting up. There's the red LED over here. So I'm not going to make you wait while it counts up to 2:30. I'll come back when it gets closer. Okay, it's got up to 1 minute. Okay, well, it's on now. I had the clips backwards. Polarity was wrong on the LED. That's pretty dumb. Now I should be able to restart this simply by pushing the load reset button again. Takes me back to the program setting of 2 minutes 30 seconds. And I'm going to start the count again by pushing the SS button. And I'll come back when it gets close. Okay, 30 seconds to go. Got my fingers around the LED to highlight where it is. Eight, 7, 6, 5, 4, 3, 2, 1. Bink, LED came on. So, that works. If you can see those two notches there, it's actually easier to see their shadow to the right than to see the actual notches, but they're two rounded notches, and that's for a lanyard or a neck strap. If you're going to be using this in the field, for example, it came with one, but you could get any appropriate diameter cord and tie it in a loop of whatever size you want, and then just open the case up and loop it through one notch around this screw escutcheon or whatever it's called through the other one and back out, so it loops around this way and back out. So that's strong enough that it won't tear out if you whip it around at the edge of the lanyard or whatever, it'll hold it. So that's what that's for, but I'm not going to do that. Alright, I found this lanyard in a pack of lanyards that I'd purchased. It's the kind that's intended to go with a digital camera, so it's got this small diameter loop, which could probably be made to work on this without any further modifications, just running that small loop through there. But I think I'm going to try to do it the way they intended it to be done. I said earlier that I think the loop just goes through here, around here, and back, but according to the instructions it has knots, so it comes in and is knotted, comes to the other side and is knotted there, so I'll do it that way. Okay, there are the knots. I think this cord is slightly bigger than the original one, but it should still fit in there. So there are the knots in there. The only other thing I have to do yet is make the splices on these battery wires. Okay, there are my wire splices for the battery. Originally there was a really thin sheet of styrofoam padding to both pad out the space between the back of the circuit board and the battery pack, but also to provide some insulation, so I think if any sharp leads or anything sticking out the back wouldn't eventually dig through the plastic outer wrapping of the battery pack and contact one of the cells. So I don't have any more of that styrofoam, I'm just using a piece of cardboard, thin cardboard. Should work just as well. These are number 4 by 7/16 sheet metal screws, black anodized, from the hardware store. They're just about the same as the original ones, which were missing from this one. I don't know if they were ever put together. It may not have passed initial testing because at least one of those major ICs was bad. So I don't know if I'm going to actually have to thread these screws in or not, or if there's already threads in there. We'll find out. Alright, here's the beauty shot. Alright, here's the final overview, post-restoration and testing. The final stop button is on the right, and the start-stop button is on the left. On the back is a chart of the different functions trying to explain how they work. Personally, I think that they're Not well represented this way. Kind of hard to figure out just from this how it works. And then on the top, the power jack is in the middle, and then the other two jacks correspond to their buttons. The start-stop jack is there on the right, nearest to the start-stop button, but it does seem that maybe the final stop jack doesn't do the same thing as shorting out the FS button. Double checking the schematic, it doesn't look like it does actually. And it's only identified in Heathkit's literature as the FS output. But then they have another diagram that says by plugging a jack or a plug into the two outer jacks and putting a switch between those, that you can effect a function that otherwise wouldn't be there. So it's a little squirrely, but yeah. Here's a picture of that light shield or sun shield that I talked about earlier. It just has these little tabs on the sides, and you kind of squeeze it and it snaps into these little slots you can kind of see there. And then it has these rectangular channels that go down to where the two displays are and block light and glare and so on from hitting them. I probably could reproduce something like that with 3D printing, but I don't think I'm going to bother. Alright, the wall wart I ordered for this finally showed up, and it looks like what was promised. 120 volts, 60 hertz input, 9 volt DC, 10 or 100 milliamps output, positive center. I have no idea how old this is. This could be really ancient, or it could be fairly current production. It came from an outfit in California. It did not come directly from China. It does have the wrong size plug on it, so I'm going to have to replace that. But before I do that, I want to make sure that this is actually working properly. So I'm going to load it to 100 milliamps and then check it with my scope to see if it has a lot of ripple or anything like that on it. Okay, there's that. And I've got my scope set up with 0 volts down there, 2 volts per division, so with the 9 volts it should be up right about here. I also have it connected to my electronic load, so I'm going to turn the power on to this device, and let's see here. The actual output is closer to 10 volts with no ripple on it, and now I'm going to engage the load, and it drops down to just under 9 volts with some ripple on it, but that's fine. That won't make any difference to the charging of the batteries. I didn't really expect anything different from this, because typically these old wall warts like that are just a rectifier and probably a little electrolytic capacitor in there, and they're not regulated, so you're going to get some ripple. And there's the 2.5 millimeter plug soldered on. Alright, I've got the wall wart plugged in, and with this type of plug, when you use the phone type plug for power, it's always important that you don't have any power on it when you plug it in, because it'll short itself out in the course of plugging it in or unplugging it. So I have plugged it in with the wall wart like that, and now I can turn this on, do a reset, and now it's running off the wall wart. Just fine. And as I usually try to do when I have wall warts for things that are dedicated to those things. I'll put on a label with my Brother P-Touch label maker. Battery charger / power supply for Heathkit GB-1201 use center socket, since they're not marked on the unit. Alright, let's take a look at the manual. This is a reproduction manual by manualman.com. It was normally a small booklet, like half of a 8.5 by 11 page, bound on the short edge, but I wanted it bound on the long edge because I buy these manuals from Manual Man without the binding. I'm putting my own binding on, but the binding I have only works on the long edge, so I reformatted things a little bit, and now it's a manual that flips up this way. So the picture of the product, it's both the GB-1201 and the GB-1201E, which is the export version. Introduction. The Heathkit model GB-1201/GB-1201E Deluxe Digital Stopwatch is a compact handheld electronic digital stopwatch. It is basically 7 instruments in one, in that a single switch allows you to select 7 different timing modes or functions. Time is displayed in easy to read digital numbers. No more will you have to interpret the moving sweep hand of an ordinary mechanical stopwatch. Events as long as 99 hours, 59 minutes, 59.99 seconds can be accurately measured to within 1/100th of a second. Use your Deluxe digital stopwatch to precisely time any event. All types of sporting events such as automobile racing and rallies, boating, flying, track, swimming, and skiing, as well as industrial uses such as machine timing, time studies, etc., are only a few of its many and varied applications. Use your stopwatch to time participants or to time the difference between participants in any event. Many outstanding features have been engineered into your stopwatch. The heart of the sophisticated timing circuitry is formed by 2 custom-designed, state-of-the-art integrated circuits. As I've mentioned elsewhere in this video, the ICs that were used here are normal ICs for the manufacturer, National Semiconductor. I don't know if there was any point when Heathkit had a part in custom designing them, but they ceased to be custom at some point. The time is clearly displayed on 7-segment numerical displays. The small, compact styling of the stopwatch provides one-hand, either right or left, operation of the start and stop functions. The handy carrying strap lets you carry the stopwatch either around your neck or by hand. Its self-contained rechargeable nickel-cadmium batteries provide many hours of reliable portable operation. In addition, a separate charger is supplied to recharge the batteries, as well as power the model GB-1201 stopwatch at locations where 120 volt AC 60 Hz power is available. Another converter charger is supplied with the model 1201E stopwatch, which allows you to charge the batteries and power the stopwatch from a 120/240 volt 50/60 Hz power source. However, the model GB-1201E converter charger is in kit form, and it must be assembled as directed in a separate converter charger manual before you assemble the stopwatch. All of these features and innovations incorporated into your Deluxe digital stopwatch to give you many years of trouble-free split-second timing. Alright, this is the parts list starting with the resistors. And larger watt resistors, smaller capacitors, diodes and transistors and integrated circuits, continued solid-state parts. Again, they referred to the custom stopwatch timer integrated circuit, but if I look at the Heathkit master parts list for 443693, it says it's an MM5865, which is again the National Semiconductor timer chip, universal programmable timer. switches and jacks, connectors, plugs and sockets, various hardware, wire, tape, and foam pads, parts for the case, and miscellaneous stuff such as the display circuit board, main circuit board, the converter charger, the 6-cell battery, the crystal, the LED, 7-segment LEDs, an IC puller, the blue and white Heathkit label, and a few other odds and ends. Assembly notes. You actually have to assemble the battery pack. The way these came is that each cell had a welded on tab, and then you had to bend and overlap where they're bridging the ends of two cells and solder those, and then wrap tape around it after putting cardboard spacers in. So you really did have to assemble your own battery pack. And then, of course, wire out the leads. Then starting to assemble the display circuit board. Resistors followed by the switches. And then the 7-segment LEDs, of which there are 4 modules of 3 digits each. Those go into sockets. Then putting in the sockets for the ICs as well as the displays. Putting in the slide switches. Mounting one diode on end, that's the one that goes to protect the battery from reverse connections. The push button switch for resetting. Plugging in the 7-segment LED modules and the ICs on the display board. Then some basic inspections of that board. And then wiring up a few wires, putting on the magnifying lens for the LEDs, putting the foam pieces on the magnifying window, and then a testing rig for the display circuit board. Powering it off of the wall adapter and doing some jerry-rigging to test out the segments and digits without the use of any ICs driving them. That's part of it, making a little jumper wire, segment testing, digit testing. And then switching it over to power it off of the batteries. Then installing the ICs in that board. Then moving on to the main circuit board assembly, starting out with diodes and the very few resistors that are on that board. There's only a handful, maybe 4 resistors, I think. There's quite a few little jumper wires. It's a double-sided circuit board, but this board is particularly dense, so they really needed an extra layer, but they're doing it with just a small plethora of jumper wires. And sockets for the ICs, which are done with socket strips instead of complete dip sockets. Little insulators around the function switch and where the crystal goes so that those parts don't short out foils on the board. Trim capacitor, 1 jumper wire that goes around this way, putting in the crystal. Assembling the connectors that form the interconnect between the 2 circuit boards. Wiring up the wires to go to the jacks. Putting on the push buttons that stick out the sides of the circuit board for start, stop, and final stop. The rotary function switch. 1 transistor, there's only 1 transistor on here that is a discrete transistor. plugging in the two main ICs, wiring up those two jacks, putting some insulating paper on the back and the top of the start stop and the final stop push buttons, springing in the red filter plastic window into the front of the case, apparently the control panel label is already part of it, that the user didn't have to put that on themselves. And there you mount the display circuit board into the case, including the jacks into the slots. Now, I previously mentioned in this video I wasn't sure how they tighten those up, and I thought they must have included some small wrench, and I made my own if I needed to do that. But here it just says tighten them up as much as you can before putting them in the slots, and then tweak the tightness with a needle nose pliers. Here's where you put on the labels on those two side switches into the plastic push buttons. Here's where you plug the two circuit boards together, put the knob on the function switch. Putting in the lanyard, putting in the rear label on the rear or bottom of the case, installing the battery pack, and it shows you how to put in the light shield if you're going to use that. Then operational tests. Test out each function with a short procedure for each one. And then operation, there's quite a few pages because of all the different modes or functions. So there's an introduction to some of the terminology used, and with a timeline for illustration. Familiarization with the display, and here's something important for what I'm going to talk about later when I go through the rest of the schematic. You've got 4-digit display without a space between them and a 4-digit display with the space. There is a virtual decimal point here, but the display itself does not have a decimal point. You just have to know that everything here is in seconds, hundredths of seconds, tenths of seconds, units of seconds, and tens of seconds. And you just have to remember there's a decimal point in between those two. And then 2 digits for minutes, 2 digits for hours. Some of these are numbered as digits. So this is digit 1, this is digit 2, digit 3. So except for the tens of hours, you can program those 3 for function 6 and 7. There's a possibility of doing 5 different digits, and those are 3 of them. And then the 2 most significant digits of the seconds, in other words, the units of seconds and the tens of seconds, constitute digit 4 and digit 5. So you cannot program those 2, but you wouldn't set those anyway because they're ripping by at very small fractions of a second. And then an overview of the controls: the start-stop button on the left, the final stop switch on the right, the start-stop jack, the power jack, and the final stop alarm output jack. And then again, digits 1, 2, 3, 4, and 5 shown again here. The function switch, the power on-off switch, the load push button, it's also the reset push button, and the display on and off switch. And then it talks about battery charging. It talks about how to use the label on the rear of the thing to remind you how to use it. Some do's and do nots. And then pretty much 1 page per function, description and illustration of what you might use that function for in the real world. So function 1, start stop with total elapsed time. Function 2, sequential total elapsed time. It's actually more like a page and a half per function. Function 3, accumulated total elapsed time. Function 4, split total elapsed time. Function 5, start stop accumulated activity time. Function 6, programmable upcount. And a page on how to program the start or stop numbers by 2 different methods. And then it continues on to the next page. That step, or that function, has several pages. And then finally, function 7, programmable down count. Pretty much the same as the programmable up count, except for the direction. Then I've already touched on this elsewhere. A few pages on how to rig up external circuits for alarming, which is used in function 6 and 7. So you know when the accumulated or decremented time matches the preset. Different ways of signaling externally through relays, or using a relay to condition a separate input and galvanically isolate it to the final stop or the start stop jack, either one. And then how to make up some external switches with the plugs, how to align it or calibrate it using instruments. Quite a few steps for that. You wouldn't think it'd be that much. There's only one adjustment. It doesn't seem to have a instruction to do it without the instruments. In case of difficulty, a couple pages of general tips, and then a couple pages of troubleshooting charts. Or there's more than that, a couple more pages. Specifications. Circuit description, 1 page, not very useful, it's overly brief. Circuit board X-ray views for the display board and the main board. That's the only problem I have with Manual Man's manuals. They don't put these in color, and they should be. They were in color in the original manuals, and they're almost impossible to use if they're not reproduced in color. Semiconductor identification charts. There's a couple different types of diodes, basically just a 1N40, 149, or a 1N914 type of small signal diode, a single 1N4002, generic PMP transistor, the couple of timing ICs, the couple of display driver ICs, the LEDs. These are apparently special. They are national semiconductor parts, but their part number here, if you look it up in the master parts list, it gives you a national semiconductor part, which if you look in the manual that covers LED displays from the mid-1970s, that particular part number is essentially a code for a custom LED display. And I think the main thing is that they cover 2 digits, 4 digits, 6 digits, 8 digits displays that are essentially the same as this, but getting it in a 3-digit display is apparently something that you have to special order, and that's why these are indeed custom parts. Although not like designed from scratch, it's just a formula that National had. They could set it up to manufacture these in different ways, because it probably is just 1 chip per digit, and how many chips do you lay on a substrate? Probably not that big of a deal. And this talks about illustrations here. Just a few things that are described elsewhere. This is for calibrating it. Just some details on display segment numbering and testing of the displays. So segment and digit testing. An assembly diagram showing how to put the side switches and their springs on, and how to mount the jacks on the case. And then there's a block diagram of the entire thing. And then an expedited parts order form. And that's it. Alright, I've already kind of touched on most of the aspects of the circuit earlier in this video, but I still want to give it a final pass just to make sure I've covered everything. So the power supply is normally just the battery. It has a fuse on each side of it, and it normally feeds through the power jack, through the power switch, and into the circuit. However, if you plug in a charger, then that interrupts the circuit here, and the charger will power the circuit instead of the battery. I mean, the battery is still connected, but it's through this resistor. This is a charge current limiting resistor. Probably also serves to have a sacrificial load if you do something stupid with the external contacts here. If you end up shorting V plus to ground, that would drop some voltage and maybe be of some use in that situation. These big circles here are just connection symbols. They're not schematic symbols in the terms of being a component or anything. So the battery is only 7.2 volts maximum. The power supply or charger is 9 volts, so there's no current that would come out of the battery into a higher potential. So the battery just sits there whenever you're connecting the charger, and the timer will run from the charger. However, because the battery voltage is lower than that, some current will go backwards through this charge limiting resistor and charge the battery. This diode here is there, I believe, primarily just in case you hook something up here with the wrong polarity, that it'll block current from going. It should go in this direction, but it'll prevent it from going in this direction. So that's the power supply. I've already kind of looked at the circuits for the SS and FS. The SS connects V plus to this line here, which goes into pin pin 13? Pin 14. And also pin 14 of this IC. So both of these main timer ICs have their pin 14s connected together into the SS switch and SS jack. Connecting those pins to V plus has the function of doing a start-stop operation on these timers. So that's pretty straightforward. The FS button connects V plus to pins 12 of both ICs, although one goes through a diode and the other doesn't. That happens when you push the FS button and you're not pushing the SS button. V plus is connected directly to this pin here and through the diode to this pin 12 here. And that's why you can't put an external switch just from here to here, because that would pull, it would try to pull pin 12 low, but it's going against the diode, so it wouldn't be able to. If you connect the external switch from the tip of this one to the tip of this one, then you are connecting V plus out of here through the switch into the tip of this one, and thereby doing the same thing as pushing the FS switch here, connecting V plus to this node. So that's why that works. The reset button, also functioning as the load button, also connects V+. In this case it goes to pin 13 of both ICs. The power switch, or the display switch rather, not the power switch, it does two things. When it's off, it connects V+ back to this point through this diode to pin 39 and to pin 39 here. So that's telling the timers that this switch is off, and that's used as a sort of a re-show the display kind of thing, where there are certain displays that when you're in a sequential counting mode you only get to see once. By temporarily moving the display switch to off and back to on, you've temporarily made a connection from V+ to these pins 39 and 39 up here. And that tells them to recycle and display the information that was previously shown. Then the other half of the switch connects between these 2 points, and those go back here. One of them is from pin 18 of this IC and back to this IC up here that's a display driver. That's the blanking input. When this pin here is connected and the signal changes, then it tells this IC to blank the display, and that's how you get the display off. Everything is still powered, but the display driver is being told to not display anything, and that saves power because none of the LEDs are being energized. This node here is the SS signal, or it's the not SS signal rather. If you're not pushing SS up here, then V+ goes through here to this point. And if you're not pushing FS, then V+ goes through this contact to here. So pushing neither of the buttons energizes this point. Likewise, pushing either of them still energizes this point. And that goes to the base of this transistor, and that in turn provides signals back into the ICs. And that's used in a couple of different ways. This is the first timer IC, this is the second timer IC. They're the same kind, they're both National Semiconductor MM5865 programmable timer ICs. Only one of them needs to have the master clock, and that's the first one. So it's crystal oscillator, very conventional, couple resistors, couple capacitors, and the crystal. Interestingly enough, the National Semiconductor datasheet has the same circuit, but they have this point here tied to V+ instead of to ground. It probably doesn't really make any difference, it just needs to be to some potential that's stable, and Heathkit decided to do it by grounding it. That's probably a little more conventional way of doing it. This is the selector or function selector switch here. It just takes V+ and connects it to any of these 7 points depending on the position selected, and those all end up going into these inputs on both ICs, these bank of inputs, and those are the function inputs of the IC, or the ICs. Also, the first 3 of them also wrap around and go up to the programming ports on this IC, but not this IC. And then there's some of the diode logic, like I've already mentioned. This is these diodes here, this diode here, these 2 diodes here, and I think at least one of these diodes here is involved with adding those 2 extra functions, because the National Semiconductor datasheets only talk about 5 functions. These programmable functions are ones that are not shown in the boilerplate examples that National Semiconductor put out in their data sheets. But obviously the chips can do it, and they have the programmability, and that's in the data sheet. They just don't explain it very much. Heathkit obviously utilized those functions and put in those extra parts and connections to make that happen. The first timer IC controls only the digits for display of seconds. The second IC controls only the digits associated with minutes and hours. So this is the display driver IC here that's providing the common pins on each of the digits. So these four lines here, these are the display driver enable signals. The four of them come down here, go around, and they're buffered, current amplified, and then they drive the commons of these four digits. Likewise, this chip here, it has the same four outputs, and they go through and again are buffered and current amplified to drive the common pins of these four digits of the display. Then all 8 digits use the same 7-segment driver that's in this IC here. This is a very conventional CMOS part, the 4511, and it just gets its signals from both of these ICs. Their BCD outputs are just wired in parallel. Well, they don't fight each other for control of the driver chip here, because they're also synchronized with each other. So each one knows when the other one should be controlling the display, and it tri-states or somehow renders effectively disconnected these 4 pins, so only one of them will be controlling this IC at a given time. And then there's a few signals that go between the ICs. This is one here. This is another one here. And this one here. Those 3 signals are ones that are used to coordinate and synchronize the 2 ICs when they're being used in conjunction with each other. I think that pretty much covers it. In case I didn't already talk about it, the charger, which they call the converter charger here, is just a simple power transformer with a full wave rectifier. It only has the 2 diodes, but it's full wave because the transformer is center tapped. And then you filter it, and you end up with an unregulated 9-volt DC output to the plug that goes into the power supply or charging jack on the timer. I forgot one connection. I pointed out 3 lines that go back and forth between these chips to synchronize them and coordinate their efforts, and I overlooked this one where pin 34 goes way up here over and back to pin 35 on this one, where 34 on this one is not used. So there's an additional piece of information, probably shared only in one direction. Alright, a little bit more on the schematic. I want to talk a little bit about the way that the digits are programmed. The display actually has 8 digits, 2 for hours, 2 for minutes, 2 for seconds, and 2 more for tenths and hundredths of seconds. There's only provision for a total of 5 programmable digits if you're using the compare function, which on this particular kit is function 6 and function 7. And they've designated the programmable digits 1, 2, 3, 4, and 5, which are probably the most useful ones. You're not going to worry about setting these ones that are just screaming past. They're so fast changing. And okay, you can't get up into the tens of hours, but short of that, you can program into the single digit hours, 2 digits of minutes, and 2 digits of seconds. And they're programmed with function switch in position 1 to program this digit, function switch in position 2 to do this one, position 3, position 4, position 5. And Heathkit refers to those as programmable digits 1, 2, 3, 4, and 5. Now, IC 101 controls the seconds, and then it cascades, overflows into IC 102, which handles the minutes and the hours. So we need to look at IC1 to see how the 2 digits here are programmed, and we need to look at IC 2 to see how these 3 are programmed. Within the IC itself, regardless of which IC it is, it's always thinking about 4 programmable digits. And it's referring to them as digit 1, digit 2, digit 3, digit 4, digit 1, 2, 3, and 4. So that's the frame of reference we have. So let's look at IC 101. Here's IC 101 on the schematic. And we see that there's a couple of wires coming into these pins here. These 4 pins, 36, 37, 38, 39, are the digit programming pins. And by the same token, the same 4 pins on IC 102. And looking at 101, function switch in function 4 energizes pin 36, which is for programming D4, and function switch in position 5 goes to 37, which is for programming D3. So we go back and look here, and sure enough, there's D3 and D4, and those are the 2 digits we're programming, and they're on 4 and 5. So yes, F4 will program D4. F4 digit 4 is what's being called D4. So you have to get past about the 3 layers of translation and what things are called, but it does add up. And then on IC 102, there's 3 signals from the function switch. F1 goes to 37, that's D3. F2 goes to 38, that's D2. And F3 goes to 39, that's D1. So once again, function switch 1 gets you D3, and there's D2 and there's D1. So once again, these 3 highlighted digits get programmed that way. When I first looked at this, I didn't see how they were getting all the digits programmed before I forgot that half the display is done by this chip and half is done by this chip, and then it started to make sense. I'd already mentioned that most of the diodes on here, D1 or D101, D102, 103, 104, 105, 106, 109. I don't remember if there's a 107 and a 108. But most of them have to do with just clearing up the fact that you have some overlapping signals where some signals are used as an input, some are used as an output on the chips, and there's the digit programming, and then there's the normal operation. Sometimes the same pins are used for 2 things. In particular, if I can find my diagram again, Here it is. This is the timer chip, of which we have two. And you can see here that 39 is for programming digit 1, 38 is for program digit 2, digit 3, digit 4. But this one also has double duty as latch control. So it's an output for programmable or program digit 1. It's an input for latch control. Digits 2 and 3 are just that. Program digit 4 is an output for that purpose, and it also indicates a waiting state. In other words, if the timer chip has been reset and is ready to go, but it hasn't been given an initial start signal yet. Because those pins can do double duty, sometimes they step on each other's crank, so to speak. And so some of the functionality of these diodes are there just to prevent that kind of thing from happening. Now these two diodes here are doing something a little different. You need to turn the comparator on in the chips when you're in function 6 and 7, because those are the functions that use the comparator functionality of the chips. So when you're in functions 6 and 7, besides doing what they normally do, those two lines come up through these two diodes, are merged. It's essentially a diode OR gate, and then it comes over here to pin 4, which is the comparator enable input. Now the corresponding pin over here, even though we still have to do comparisons, it isn't driven directly off of that. But when this chip is put into compare mode, and when the comparator is on, this pin here, pin 12, is the final stop input, but it does double duty as a comparator out. So it's another one that can go either direction depending on what mode the chip is in at the moment. And that comes over here and goes to pin 4. So you're commanding this one to turn its comparator on, and that causes this to become an output that turns this one's comparator on. So that's how that works. I wasn't really sure what the function of this diode here was. Heathkit actually does mention this one. They describe so little in their circuit description in the manual. I was surprised they bothered in this case. But they said there's a situation involving when you have the comparator function on, and especially when you're doing digit programming, that you might get a false comparator output coming off of pin 12. And that can in turn influence things here in ways you don't want to influence them at that point, so that diode blocks that from happening. That's its function. And this does something similar, D109. When you're in digit programming mode, the alarm function coming out of comparator output here can hash things up. So again, this diode blocks that from happening. And there's also a little bit of logic done here where there's not enough room on the board to put another logic IC, so just like this, where instead of putting a chip with an OR gate on it, they're just doing it with a couple diodes. And also this transistor is doing a logic function. When the SS switch here is not pressed, then this connection is made from V plus up through here, down to here, over and to the base of this transistor, which is a PNP type. So normally the base of this PNP transistor is pulled low by this resistor, and pulling that low turns the transistor on. But when the SS switch is not being pushed, we get V plus to come through here, and it pulls the base up against the tendency of the resistor to pull it down. When we pull it up, the base is at a high potential, and therefore the transistor can't start turning on, therefore it's off, and therefore this resistor is pulling the collector low. With this transistor off, there's nothing to pull it high, so the resistor pulls it low, and that goes over to the function 6 switch position and pulls it low. But when SS is pushed, now it's going down to here, so this point is left floating. So this resistor pulls the base low, which turns this on. And since this point is connected to V+, now it can pull this up against the tendency of this resistor to pull it low. And so now the F6 line is high. So essentially we've taken the action of the SS switch and inverted it and used it to feed the F6 line. But the way we're doing it here doesn't mess up the switch's own ability to pull F6 high when it needs to. So there's a couple different things pulling on F6. And that gets into the weeds on how the digit programming works. So I've decided to do a bit of a supplement here and actually go through the MM5865 pinout and describe some of the interesting ways that this chip works. It has quite a lot of capability and flexibility. So normally I don't go into the weeds so much on the individual ICs when I do these Heathkit documentaries, but in this case I'm going to. First we have to deal with the power supply. The pinout is unconventional in this regard, although pin 40 is VSS and that is the V+. For this particular chip, and VDD is the ground, circuit ground. Sometimes you'll see VSS and VDD kind of upside down for that, and indeed about half of the references in the pin descriptions in the National Semiconductor data sheet have them reversed. They're not consistent about what they're calling VSS and VDD. So I don't know if they have a copy and paste issue from some other document or different people writing different parts of it and one of them had them flipped in his head. I don't know, but it is confusing. And the chip is designed to work with a difference between VSS and VDD of between roughly 7 volts and up to 15 volts. On the Heathkit GB-1201, the VSS is no more than 9 volts and nominally 7.2 volts from the battery, but it can be less than that as well. At least down to 7 volts, it's good according to the spec sheet, and it'll probably work lower than that. So we've covered that and this. I'll just strike them off as we get to them. So let's start with the function 1, which is on pin 5. So I've already described what the different functions do briefly in a different part of this video, so I'm not going to repeat that part of it here. But when this pin is high, logic high, in other words, pulled up towards VSS, then the chip is going to be in function 1, and the way its counters work, the way its other pins work, will all be in line with that particular functionality. So we'll get rid of function 1. Same thing for function 2 on pin 6, function 3 on pin 7, function 4 on pin 8, function 5 on pin 9, function 6 on pin 10, function 7 on pin 11. Now let's look at the reset on pin 13. Whenever you energize that pin, it resets all the logic and counters in the chip if you're in functions 1 through 5 or function 7. However, if you're in function 6, the reset signal will reset the logic but will not reset counter C1 or counter 1. The reset pin is internally pulled low, in other words to VDD, through an internal resistor. For a reset to occur, pin 13 must be pulled to a logic high, in other words to the same potential as VSS. Let's look at the start-stop signal on pin 14. This input is used to control the counters. How it affects the counters depends on the function, and I'm not going to go into all the details here on what the individual counters inside each chip are doing in every function. It's needlessly complicated for the scope of this documentary. But again, the start-stop pin's main function is to start and stop one or more of the timers that are counting during timing operations. It's internally pulled low, in other words to VDD, through a resistor, and you need to pull it high, in other words towards VSS, in order for it to function as a reset. Now we get to pin 12 here, and this is the final event stop as an input on that pin, or the comparator output as an output from that pin. Does double duty. As an input, this pin indicates to the chip's circuit that no more events will be timed or counted. It affects the circuit when it's pulled to logic high, in other words VSS, and there is an internal pull-down resistor to VDD. This pin is also an output, which is the comparator output, and in this situation it is normally low, in other words at VDD, and goes high, in other words to VSS, when the two counters, counter 1 and counter 2 in the chip, have the same value. Let's look at the divide scaler inputs. There's 3 of them on pins 1, 2, and 3. These 3 inputs determine when counters C1 and C2, when they will count in modulo 6 or modulo 10. If you don't know what modulo 6 and 10 mean, that refers to the range of numbers that a character in a number can have. For example, if you're set to modulo 6, then that character can go 0, 1, 2, 3, 4, 5, which is 6 possibilities, and when it actually gets to 6 it resets to 0, so it's not really doing 6, it's just 0 to 5. If you're in modulo 10, that's what we're used to in base 10 numbering, where you go from 0 to 9, and if you overflow that to a value of 10, it can't be 10, so it just overflows to the next digit and resets itself to 0, so you do 0 and 9 again. Because this is a timing counting chip, some digits in times need to be in modulo 6. In other words, if you're counting seconds in a minute, you can go up to 59 and then it rolls over again. So if a digit can only go to 5, it needs to be in modulo 6. But if the number can go up to 9, it needs to be in modulo 10. So there's a whole table in the data sheet, and depending which combination of these pins you have, high and low, you can put different parts of the chip into modulo 6 or 7 or modulo 10. It treats signals that are held at VSS as a logic 1, and if they're tied to VDD or left floating, there's an internal pull down to VDD, then they are logic 0. On the Heathkit GB-1201, IC1 has its divide scale inputs 1, 2, and 3 set to logical 1, 0, 0 respectively. And as this IC controls the lower set of 4 LED digits, representing from right to left, 1/100th of a second, a tenth of a second, units of seconds, and tens of seconds. Those digits respectively have modulos from right to left of 10, 10, 10, 6. So it can count up to 5999 before rolling over. So that is actually 00.00 seconds up to 59.99 seconds. So that's what we get on IC-101 by programming it as a 100 pattern on there. On IC-102, that's controlling the other 4 digits on the display, and it has its divide scale input set to 110 respectively, and as this IC controls the top set of 4 LEDs representing from right to left the units of minutes, the tens of minutes, the units of hours, and the tens of hours, that digit pattern respectively gives you a modulo from right to left of 10, 6, 10, 10, allowing counts of 00 hours, 00 minutes, up to 99 hours and 59 minutes. Next one we're going to look at is comparator enable. This input enables the comparator used in functions 6 and 7. When this input is held at logic 1, which is the same as VSS, the comparator is enabled, and it is disabled when the pin is held at logic 0 or VDD, and there is an internal pull-down resistor to VDD for that pin. Now let's look down to position 16 and 17. Resolution select. These are inputs. They're used to select the frequency of the clock pulses that are fed to the internal timers C1 and C2. These inputs have integral pull-down resistors to VDD and are active when you pull them to logic 1 or logic high, which is the same as VSS. On the Heathkit GB-1201, IC-101 has its resolution select input set to 00. They're actually floating, they're not connected to anything, but when they're floating, then the internal resistors pull them to logic 0, so that's how they get that 00 pattern, which means that the counters in that chip are fed from a 100 Hertz signal, which is divided down from the crystal oscillator, and that gives you a timing resolution of 0.01 seconds, which is appropriate given the counting range of the counters in that chip. Now for IC-102, it has its resolution inputs selected to 1-1, which means that the counters in that chip are fed from an external clock rather than the internally generated clock. Normally the clock in and clock out pin on that chip, which is pin 15, we're not there yet, is an output, but when both the resolution select inputs are set to 1-1, that same pin, it becomes an input. And this is appropriate since that chip is used in a cascaded manner, slaving from IC-101, which is the master. To facilitate this, IC-101's clock line output from pin 15 is connected directly to IC-2's clock line input, which is also pin 15. Whether the clock in-out pin, pin 15, is an input or output depends on what pattern you put on the resolution select. Now let's look at the blanking input on pin 18. This is an output actually. It's used to blank the associated display at the beginning and end of each digit time to allow for internal delay between two cascaded chips. So this is important when you've got the two chips like this hooked together in a cascaded manner. The display is blanking when this output is at logic 0, in other words, a VDD level. On the Heathkit GB-1201, only IC-101's blanking output is used, since it is the master of the two timing chips. It is not connected directly to the display segment driver. Rather, it is connected there via the display switch. When the switch is on, the blanking output is connected directly to IC-201's blanking input. And remember that IC-201 is the driver for the LED display. When the display switches off, IC201's blanking input is connected to circuit ground, thus always blanking this display even though IC101 might be otherwise trying to unblank the display. So you've got a physical switch on the control panel overriding what these chips are trying to do in certain situations. And that's all I really need to say about that. Oscillator in and oscillator out. One of the two timing chips in a circuit like we're doing here, where there's two of them and they're in a cascaded arrangement, one of the two chips must have an oscillator. If it doesn't have its own oscillator, then it must be configured to use an external clock. On the Heathkit GB-1201, IC101 does have an oscillator, and it's connected up to those two pins. Or it's actually part of the oscillator, but the external components required by the oscillator are connected up to those pins. But on IC102, it does not have anything connected up there. It's getting its clock signal from the first chip, the one that does have the oscillator. So internal to the chip there's a pair of FETs that are used as an inverter and a buffer. The buffered inverter is connected with its input to pin 19 and its output on pin 20, hence the in and out there. Normally connected between these two pins are a resistor and a 32.8 kHz crystal connected in parallel across those pins. There must be a small adjustable capacitor from pin 19 to circuit ground and a small fixed capacitor from pin 20 to ground. And the adjustable capacitor just allows fine-tuning of the crystal to get it exactly to 32.8 kHz. The next two pins we're going to look at are multiplex in and multiplex out on pins 23 and 22 respectively. The multiplex input, pin 23, allows an external multiplex rate to be used in the chip. The multiplex rate inside the chip is 1/4 of the frequency at the multiplex input and multiplex output rate. When using the multiplex input, the multiplex output must be tied to circuit ground or VSS. The multiplex output is 4 times the internal multiplex rate. To use the multiplex output, the multiplex input must be tied to logic high. If a given chip is using its multiplex input, then the multiplex output must be tied to logic high or VDD. And indeed it is on the GB-1201. To use the multiplex output, pin 22, the multiplex input on that chip must be tied to logic low or VSS. And again, it is on the GB-1201. Now we have the pins that are primarily used for coordinating the two chips together when they're cascaded. There's control C1, that's for counter 1. So C1's control input on pin 35, C1's control output on pin 34, C2's control input on pin 24. I may have said 24 up here, it was supposed to be 34. And then C2's control output on pin 25. And those get interconnected together. So again, these 4 pins are used to cascade 2 chips together. When the control C1 in pin, that's this one up here, is floating, it has an internal pull-down resistor to VDD, or if it's actually tied to VDD, the clock pulses to counter C1 in that same chip are inhibited. When the control C1 in pin is high, in other words, the same potential as VSS, then C1 is enabled to count. The control C1 output is high or VSS, when C1 is at its maximum count, and all other times it's floating. In other words, it's like it's internally disconnected. The control C1 input must be floating or connected to VDD while programming digits in function 7. The control C2 input and control C2 output pins operate in the same manner for counter 2 as these two pins do for counter 1. Here's how those pins are connected on the GB-1201. Some wires connect back and forth between the chips, but I redrew it here just to make it a little easier to follow. IC 101's on the left, 102's on the right, so this is the lower order chip, and then it cascades up to this chip. The C1 in and C2 in are just tied to VSS or logic high, and so those being pulled high allow counters 1 and 2 to operate. They're not inhibited, in other words. And then C1 output cascades up to C1 input on the next chip, and the output of that is not used. Likewise, the C2 output on this chip cascades or overflows up to the C2 input on the next chip, and the output of that counter is not connected to anything. So that's logical. That's how you can overflow counter C1 in the first chip to C1 in the second chip, and C2 in the first chip to C2 in the second chip. Alright, let's get to these 4 pins up here. These are program digit 1, digit 2, digit 3, digit 4, with 2 of the pins doing double duty as mentioned elsewhere in this video. So pin 39 is program digit 1, 38 is program digit 2, 37 is program digit 3, 36 is program digit 4. These 4 inputs are used to program or set any desired count in counter C1, and that's because if you're in functions 6 and 7, where you're using the comparator, C1 is used as the reference and C2 is the one that's actually going to count or time, and then when it matches the value on the reference, or C1, that's when you have a comparison and you know that you're done. So, for example, when program digit 1, pin 39 is high, or VSS, the least significant digit of counter C1 will advance at a 2.5 Hertz rate. There is no carryover from digit to digit. Program digit 1 has no effect if tied low, in other words to VDD, or left floating, and there is an internal pull-down resistor to VDD. Only one program digit input may be held high, in other words at VSS, at a given time. Now, I already covered elsewhere in the video how that works. The 2 chips are controlling a different number of displayed digit or program digits. C102 has got 3 digits it's using, and 101 is using only 2 program digits. So these are tied differently on the 2 chips, but it all comes down to what I already showed in my little diagram right here about how those are programmed and which function switch positions end up programming which digit on the physical display. So I'm kind of repeating myself here with these 4, so we can check that off the list now. Now for the program digit or program digit 1, now for the program digit 1, it also does double duty as the latch control here on pin 39. So besides setting a count in digit 1 of counter 1 when in function 6 or 7, this pin also affects functions 3 and 4. In those 2 functions, this input will allow the display to show, or will allow the display to show the value that's currently in counter 2, as it's counting, and that's as something that is unique to functions 3 and 4. Normally you can't see counter 2 in action for most other functions, but in functions 3 and 4 you can see it at some times while it's actually counting. And that's how you get that, by using that pin in that way. But if you're in functions 6 and 7, then this pin functions in its normal mode as a programmable or program digit 1 control input. Finally, we have the so-called output circuits. BCD1 on pin 33, BCD2 on 32, BCD4 on 31, and BCD8 on 30. Remember that in BCD they're binary weighted, so each one's double. A 1 doubles to 2, doubles to 4, doubles to 8. So those are the binary weights of those 4 pins. And those are designed to go directly to the input of the display decoder driver, which takes the BCD code coming from this IC and converts it to one of 7 segments, or not one of, but whatever pattern of 7 segments is required to display the appropriate digit that matches up to the BCD value of those 4 pins. And you can use only one such decoder chip, because if you're cascading 2 of these chips, they already shift gears internally and they only output BCD code on these 4 pins when it's their turn in the overall display multiplexing scheme. The other output pins are digits 1 on pin 29, digit 2 on pin 28, digit 3 on pin 27, and digit 4 on pin 26. These are ones that are not tied together, so each of these chips controls its own 4 digits of the display directly in terms of enabling the digits in their multiplexing. Whereas these pins, if you've got 2 of these chips, they're tied together, so pin 33 on one chip's tied to pin 33 on the other chip, and then onto the decoder driver, and likewise for the other ones. But here, these go only to the buffers that are driving the common pins on the display digits. And then there will be a separate 4 wires for the other chips, digits 1 through 4. So those are not paralleled. Alright, I'm going to attempt to build a rough and ready sunshield for the GB-1201, and inspired by the original design, which I don't have an example of, I've just taken a few measurements and tried to figure out the simplest, quickest way of doing it. And I've decided I've got this trapezoidal 3-dimensional shape, like a wedge-shaped box that's sized to fit the window of the GB-1201 and come up about 20 millimeters. It actually measures 38 millimeters wide at the bottom, 48 millimeters wide at the top, with a rise between those of about 38 millimeters. So pretty simple dimensions. And it's just going to be a 5-sided box. So I'll create that by making a solid object. Hopefully Tinkercad will let me in that shape. And then make a smaller version of it that's 1 millimeter smaller on the 4 sides and 4 millimeters thick on the top, just so there's at least one stable side with more than 1 millimeter thickness. And then I'll put that in, make that out of negative space and put it inside the first one. That'll give me the 5-sided box. And the only side that is open will be the bottom. I'll put a couple of little rectangular shapes in there for the tabs. Just to keep it simple, I'll make them not parallel to the wedged sides or the tapering sides. I don't think it'll make any difference. And then I'll make a couple of boxes like this that are just a solid six-sided object with negative space six-sided objects inside of them. They're just a bit smaller, so it'll end up being like a four-sided box, a larger one for the rear, a smaller one for the front, and then just put those inside the trapezoid, and that should create the two passages through which light will pass. And hopefully it's no more difficult than that. Well, there's no regular basic shapes to put together to make something like a trapezoid, but there is this tool I've never used before. It's called the extrude sketch mode. I've got my grid set up to 1 millimeter. Everything on my shape is 1 millimeter. So I'm going to grab this tool and drag it onto here. And it's what's new. You can... video can't be played because the file is corrupt. That's on their own help. Oh dear. So now I'm in the sketch mode. I don't see the workspace anymore. I have basically a like a grid of the drawing, and I can basically draw what I want in 2 dimensions, and then it'll automatically be rendered in a 3-dimension by making it 10 millimeters tall, or something based on the grid, I think. And since I just need the trapezoid, I should be able to draw that shape and give it a height of 20 millimeters, and there will be my shape. So I'm going to try that out. Alright, there I drew the trapezoidal shape. It only gives me one set of dimensions, 48 total width, which is what I wanted from my sketch, but it's giving me the greatest dimension, and it's giving me 38 high, which is what I wanted, so that's good. And since I have this centered on this central line, it's 10, 19 wide, 10, 19 wide on each side, so 38 across here, which again is what I figured I needed. So hopefully that's all I have to do now. And I'm going to exit sketch mode by clicking Finish Sketch. Alright. So it shows it as an extrusion up here. And I've got all this stuff here. I have a quality of 12, whatever that is. A height of 10 by default, that's 10 millimeters. I'm going to crank that up to, well, I'm just going to type it in here. I want it to be 20 millimeters. Top scale, base scale, there's no twist to it. But it looks like it's more or less what I want. Alright, it looks like the shape I want. That was pretty easy. Good to know about that particular tool. Now I've gone from the sketch tool to the regular work plane tool, and the object I've just created is depicted like this, which is a little confusing because it shows the two-dimensional shape, but then it has the normal workspace or work plane tools for dimensioning, but they're kind of offset, which is kind of odd. Like it doesn't know where to put them. But if I click on them, it does show the total height of the object is 38 millimeters, the total width is 48, and I need to click click on that part to see the height, which is 20 millimeters. So it does appear to be correct. Okay, I've made another sketch. This will be for my negative space, and it has a overall dimension of 46 millimeters, which is correct for my smaller trapezoid, and a height of 36, which is correct. So I think that's good. Have to double check my dimensions because it doesn't show me the bottom dimension. It's 10, 2 points short of 20, so that is 18, and 18 on the other side, so that is the 36 dimension I need there. Good. So I'll finish the sketch and it'll appear in here. And all I have to do go here is change this to 20, and now I've got that object. It should be just ever so small. You know, smaller than the other one by 1 millimeter. Except I made a mistake. This smaller one is only supposed to be 26 millimeters. Well, that's not right. It can't be 26 millimeters. It's supposed to be 16 millimeters because the other one's 20. It needs to be 4 less, so I need to change this to 16 millimeters. Okay. And also change it into a negative space. Oops, what did I do here? So I'm going to roll this back down to a more vertical view and just drag the smaller negative space one more or less like this, surround them both, and click do it again, I messed up. I've got the help tools popping up and annoying me here. I need to do the align tool, do a vertical alignment and a horizontal alignment so the two are there. I can't see the smaller one anymore because it's behind the bigger one, and now I have to group them. So now it's a single object, but I can't see the recess in the bottom because I'm looking at it from the top. So I have to roll her over, look at it from the bottom, and there it is, in fact, the big empty 5-sided trapezoidal box that I wanted to have. Very good. So now I've added the positive and negative space rectangles for the light channels. I've got to check my dimensions. The big one should be 12 by 32. It is 12 by 32, and the one inside should be smaller by 2 millimeters, 10 by 30. Good. The smaller one should be 12 by 26. 12 by 26. The other one should be 10 by 14. Or not by 14, 10 by 26. Or 10 by 24, that's what I meant to say, yeah. 10 by 24, and that's what it is, instead of 12 by 26. Yes, those dimensions are correct. So now I just have to group those two and align them with each other, vertically and horizontally, and group them. And do the same thing with this. Align them horizontally and vertically and group it. And I can see that they are the desired shapes. I'm going to change this one. I'm going to leave that one as red. That's okay. I'm going to make this one a different color, like some sort of blue. There we go. Now I just have to position those appropriately inside the trapezoid. They'll be centered horizontally, and I can align them along the bottom and then do a vertical offset to move them in the Y direction the exact amount I want. Okay, I have positioned those. These are the same height as the overall trapezoid. If I merge them or group them with the trapezoid, then I should have the desired shape. Let's see what happens when I do that. Group everything and then do a group. But it's not visible. Let's see. Is it there on the bottom? Yes, it is. But it's not poking through the top. Did I make a mistake and not make these tall enough? Possibly. Well, I've gone back and re-edited the two rectangular sections to be 22 millimeters taller so they would poke through the top. I thought that would give me negative space here and here, but I think what it's doing is I think the solid top of the larger trapezoid is superseding the negative space on the inside of the two rectangles, so it's considering this to be positive space instead of negative space. I thought that bringing these into the larger one would have these negative spaces also affect the trapezoid and thereby make an opening here, but it seems that it's not working the way I thought it would. So making these taller wasn't really the solution. And I can see that, you know, they are taller. And that's not what I wanted. I don't want the darn things to stick out through the top. So I need to go back and revise those once again to be the desired height. And then I'm going to have to create new negative space objects and put them inside of this in order to make holes in the top. Alright, I put everything back together and I've added two more negative space 3D objects that match the internal dimensions of these two boxes. So if I group everything, now I finally get what I wanted. Good deal. Does it look right if I tip it up? It does. If I look on the bottom, I've got the shape I want. It's only 1 millimeter thick on the walls. I'm hoping that's springy enough to allow me to flex the sides in enough to get those in place. So now I have to add those little tabs and I should be done. Okay, I've made my little tab here. It's 1 millimeter high by 7 millimeters tall, and I believe that's what I measured. It has to go from 15 to 22, so that would be, yes, 7 millimeters, and 5 millimeters wide. 2 millimeters is on the outside at the top and 3 on the inside, and then at the bottom it goes to something more like the opposite because it's on a taper. So very good, it's the right size. Now I just have to make a couple of them. Just made a copy. And now I got to put them in place. Okay, there's the tab. Oops. Control Z. The other one's over on the other side. I was debating about how much I wanted those to stick out. But I'm on a 1mm grid, and because of the angle, I'd like it to stick out just a hair more, but it's sticking out plenty down here, so I think that'll be enough to hold it in place. I don't want it to be sticking out too much. Alright, so let's see here. Surround the whole thing once again. Group it. And now I have my desired shape. Good. And I've got my GB-1201 sunshield.stl file. It's getting kind of late in the day to start printing it, so I think I'll do that in the morning. So there it is in my Prusa slicer. And again, I can move around and see it from different angles. Looks like it came through the process all right. So now I will slice it. And look at the result. We definitely have the open space there. That green jaggy thing, I believe, means there's support material in there. And I think that's because the roof here is not got anything under it, and it'll print just the walls of these two and the outer part up until it gets to the roof, and then it's decided that it needs to print something in that space to support the roof while it's printing it over. I was a little bit unsure of how much it would bridge without doing support material, but it does look like it's planning to put some in there. So we'll see how that works out. Alright, the 3D printer successfully printed it. It does have the holes through it, like I expected. There is some garbage around here which is apparently part of the support structure. I don't know why it did that on the outside. I would expect it to be on the inside, and I imagine it is. I didn't watch this during printing, so I'm not really sure what to expect when I break it off of the plate here. Probably what I should have done is print this face down so that it would have a nicer finish on the top. It would still have to probably print a support structure for these tabs, but that would be less support structure than it has to do to support this as a roof. And you can see all the support structure on the inside that's designed to be torn out of there. Alright, I pulled the support structure out of it. This is all the stuff once you peel it out of there. Just grabbed it with the needle nose and tugged. I'm going to check it for fit. And if all looks good there, then I'll tell the Prusa slicer to print it or reorient it upside down, and I'll print another one. Only took an hour and a half. There is pretty good spring to these sides. I can definitely squeeze them in. So if I put this on here, stick one tab in. Yep, it does snap on like planned. Now I just want to see if it lines up with the displays correctly. So I've got my lamp here shining on it, and it definitely can't get back in there to glare the display out. It definitely works as a sun shield. I'm just going to wait till it rolls over to the top display, make sure that is more or less centered in the chamber, and if that is, then I'll go ahead and print an inverted one of these. Almost there. Yay! And you can still have it at a fairly good viewing angle and make it out. So I think I guessed about right when I took my measurements. Wunderbar. Okay, I'm back in Prusa Slicer. I've got my object there again. I'm going to roll it over 180 degrees on the y-axis. And yep, sure enough, it now has it face down with the mounting tabs facing up, and the roof is on the bottom now, so that should come out printing better, but it'll probably need to make some support structure to hold these tabs up when it gets around to printing them. Everything else is just a vertical wall that don't need support structures. So I'm going to go ahead and slice this, and sure enough, it shows that it'll build a support structure on the sides for that. That's what I should have done the first time. And the estimated time for printing is about 15 minutes shorter than the other way around, and I suppose that's because it doesn't have to print such an elaborate support structure all through the object the way it did the other way. Alright, here's how it came out. Still has the support structure there around the tabs. It is a somewhat more even looking face on the front. Let me just pull those support structures off. There we go, that came off pretty as you please. I'm left with the tabs. Yeah, this is definitely the better way to print them.